Hi folks, we are on Unit 1, Day 8, and this is the first video. So in this lesson, we're going to start talking about not just what algebraic vectors are or how to draw them, but we want to be able to do some math. We want to be able to do the same kind of operations that we've been doing with the geometric vectors, like for instance adding vectors together or multiplying vectors by scalars. We want to be able to do that with our algebraic vectors, and we will find that the process for doing that, once we figure out kind of these techniques, is actually much easier with algebraic vectors. So these tend to be easier to work with because they are a little bit more theoretical, and we can come up with some pretty straightforward equations. So just a review here, we talked about how to write a vector going from the origin to a point as the coordinates of the point where that vector would end. And again, vectors have, you guys are going to get sick of hearing this, they have direction, they have magnitude, they do not have position. So we can reorient any vector in space and just arbitrarily say, I'm going to start this vector at the origin, because then I can write the vector very simply as the point where it would end if starting at the origin. So you kind of take any vector anywhere and scooch it over to start at the origin. We also talked about the idea of component vectors, which is going to be a big concept for today, and that we can break down any vector into its component parts. So we can talk about the amount north and the amount east of velocity headed northeast, for instance. We can talk about a horizontal force and a vertical force of a force that's acting at an angle. We can calculate those. So what we want to do is come up with a more useful way of working with these algebraic vectors in R2 and then extending that to R3. So this is one of our diagrams from yesterday, talking about how the vector goes a certain amount in the x direction and another amount in the y direction and ends up going to point AB from the origin. And what we want to really do is think about how we can represent these in terms of x and y. And one of the things we do to make this easier is to define two special unit vectors as I and j. So I is going to be the unit vector in the direction of the positive x-axis. So I is the vector 1, 0. And j is the vector in the direction of the positive y-axis. So 0, 1. So if you're starting at the origin, this one goes 1 unit right in the positive x, and this one goes 1 unit up. And hopefully you guys can see kind of where we can take this, that now, kind of flipping back to that previous diagram. So that would be vector I going 1 unit along there, and that would be vector j going 1 unit along there. So we can break these component vectors, the x and the y, up into a scalar multiple of a special unit vector. So what we want to do is to write any vector OP in terms of these unit vectors I and j. So we're going to take writing the vector OP in terms of our x and y we started with in the previous diagram. So if we have OP, we talked about that was some component in the x direction plus some component in the y direction. And whatever these magnitudes are, we can say that this is A, because we go A units in the x direction, times vector I hat, plus B, which was our value that we get to in the y direction, times vector j hat. So we're going to break this up into multiples of the component vectors. We'll be able to do this for any vector in R2 and eventually in R3, and then being able to write all vectors as the sum or the linear combination of two known vectors is really, really powerful, because then we can use all of our vector operations and the vector properties on these and come up with some more easier ways of calculating things with the algebraic vectors. So two important things here is the difference in form. So we know that vector OP can be written as A comma B, and it can also be written as A times I hat plus B times J hat. When you're answering questions on algebraic vectors, it may specify component form or unit vector form. So this is unit vector form here. So you need to be able to answer your question and give your response in the correct form. In particular, in this unit, I will probably stop specifying. In later units, it's not as important, but you do need to be adept at kind of swapping back and forth between those two forms. So pretty easy here. We're just switching. This one is in component form. We want to write it in unit vector form. So this goes -2 in the I hat direction. So it would be -2 I hat and -5 in the Y direction. So -5 J hat. So that's just converting from component form to unit vector form. Likewise, this one, it looks a little bit messier. It goes √3 in the X direction and pi in the Y direction. So remember those, obviously irrational numbers, but just numbers. So we can convert that to component form. So you really need to make sure that you're able to convert between the unit vector form and the component form. And just kind of being aware enough that when you're doing solutions to problems, if it asks for a specific form, make sure you're writing your answer as it's required. Extending this a little bit to R3, we've got I, we've got J, and now K. So K hat is probably not unsurprisingly, that's going to be our unit vector in the Z direction. So we can do the same things with algebraic vectors in R3, just extending that. Instead of just the 1, 0, it's 1, 0, 0, because in R2 we're only working on that XY plane. And J hat would be 0, 1, 0, and K hat now is 0, 0, 1. So K hat is a unit vector in the positive Z direction. So we can write every vector in R3 as a linear combination of I hat, J hat, and K hat. So if this was OP, if it was A, B, C, we would say that's A times I hat plus B times J hat plus C times K hat. So it's just extending it with one more variable when we're working in R3. So if we were adding algebraic vectors, what we want to do is think about how we could kind of define vector addition. So I'm going to make two vectors. Let's say OA is given by AB and OD is given by CD. If I want to add these, this, remember, could be A times I hat plus B times J hat, and this one would be C times I hat plus D times J hat. So we're going to use our properties of vectors to add these together and come up with an expression for how to add algebraic vectors. And it is a lot easier, a lot easier than, having to draw them out like we did with geometric vectors. So A I hat B times B plus B times J hat plus C times I hat plus D times J hat. Remember that vector addition is commutative, so we can change the order around here. So we get A I hat plus C times I hat plus B times J hat plus D times J hat. And we know that we've got that distributive property that we talked about. We can kind of collect like terms. So this would be a plus c times I hat plus b plus d times j hat. And converting this back to component form, OA plus OD is just a plus c, comma, b plus d. So really, if we have two vectors in component form and we want to add those vectors together, we can actually just add the x values and add the y values, and that will give us the sum of the two vectors. And the next page has an example of that. We can add these vectors. So OA plus OB, it would be 6 plus -7 in the x, and you obviously don't have to show this every time, and 1 plus 4 in the y. So we get -1 and 5. Okay, and we could restate that in terms of I and j. It would be -I hat plus 5j hat. So you can draw out also what that would look like on a graph and kind of see how that works. And I will include a graph in the notes.